series of talks. I just want to introduce Rachel Priest, is our other organizer that just plugged in, and David has an announcement.
All right, so I forgot to say earlier, the videos from these talks should, in theory, be up on the web by the time dinner is over. So if there's anything you've missed and want to go back and look at it again, that should be there and available to the website.
I will also provide a link to my website of the slides.
Ah, great. Yeah.
And I can also send them to you.
Great. So then let me introduce Victor Rotger from Barcelona to speak on Stark-Heegner plates.
Okay, so thank you very much. Do you listen to me well? Okay. So we are supposed to talk about Stark-Heegner points. These are generalizations due to Henri Darmon of the classical Heegner points. And there is not a single definition for them. There are many different constructions. So in this lecture, we will be talking about some of these constructions. And I will start here recalling the very basic facts about the classical Heegner points on elliptic curves. And I will rephrase this classical construction in several ways so that it leads us to one of the generalizations, which may be called Stark-Heegner points, or people also call them Chow-Heegner points, as Bertolini, Darmon, and Prasanna call them in their papers. So that's what I will be explaining today. Henri will explain other constructions tomorrow of Stark-Heegner points. And then we will continue with a very specific example, which is related to triple L functions, which will be also the goal for the evening sessions, computing them explicitly with the modular symbols that Rob just explained to us. So it really fits quite well. So, okay, so I don't see very much what is here. So let's start with classical Heegner points on an elliptic curve. So we consider an elliptic curve of defined over Q. So we now know that this is modular, and there are many ways of phrasing this. So one possibility is saying that the L series of E of the elliptic curve is equal to the L series of cast form of weight 2 with rational Fourier coefficients. So F is the modular form associated to E. And when you have this, you can recover the torus, the complex points of the elliptic curve as a lattice, as a complex modular lattice, where this lattice can be computed using these periods that Rob was explaining before. So here you just integrate your modular form that you can regard also as a differential form, as a holomorphic differential form on the modular curve, and you integrate it against all possible paths on the modular curve, and this gives you a lattice, which is naturally embedded in the complex numbers, and this is the lattice which induces this isomorphism between the elliptic curve and this torus. And when people say that E is modular, you can say, as I said before, these two L series are the same. But there is another way of phrasing this, which is equivalent. Let's call it the geometric version of modularity, which is that there is what people call a modular parametrization, which is a map of curves, of algebraic curves. X naught of n here is the classical modular curve of level n. And this is a map which is non-constant. It's defined over Q. And analytically, if you see this over the complex numbers, this modular curve is the upper half plane when you adjoin some cusps, modulo the action of gamma naught of n. And this map sends, for instance, maps the cusp at infinity, what Rob was calling I infinity, to the zero element of the elliptic curve. And any element tau in the upper half plane, or cusp, you map it to what I will be calling a p tau. And this is just integrating as Rob was doing before. The only difference is that my tau here can be a cusp, for instance. This is what was being done in the first lecture, or any element in the upper half plane. Okay, and this is the point you get. So this is a recipe which is purely analytic, but this map, this is really a map of curves defined over Q, and this is just the expression of this map on the complex numbers. But you should keep in mind that this is this arises from a map of curves which is defined over Q. Yes.
So if I change E to an isogenous elliptic curve,
Yes.
the same F. So is this lambda F is given the optimal or?
Yeah. Okay. So this is sure. This is isogynous. I said isomorphism, but this E. That's why I didn't write isomorphism. Okay. So any two elliptic curves which are isogynous, they all have the same LCDs. So this is only defined, say, up to isogeny. Okay. So this F only determines E up to isogeny. Okay. So if we take tau to be a cusp, then I get this point. These points turn out to be rational points, and they also turn out to be torsion points. This is a theorem of Manin. And if I now take tau, which is in the upper half plane, this curly H is my notation for the upper half plane. But I also take it to land in some imaginary quadratic field, K. Then you can compute this P tau. And the theory of complex multiplication proves that this is actually also an algebraic point. This is not it could well be a transcendental point on the elliptic curve, but not it's rational over some abelian extension of K. And this is like the main application of the theory of complex multiplication to elliptic curves. And let's explain a little bit which is the more precise formulation of this, and a little bit also of the proof. So when you take this tau, you can form this lattice which is Z plus Z tau. And if you look at which are the automorphism of Z which preserve this lattice, you realize that this is in one-to-one correspondence with the following set, which this will be a ring. So any lambda, which now lambda is any complex number, which preserves the lattice, lambda preserves the lattice if and only if there is some gamma. Gamma here will be any matrix with integral coefficients such that n divides the lower left-hand entry, and such that when you make gamma act on this vector, tau 1, this vector is an eigenvector for this action. And the map which maps gamma to lambda embeds this ring which into a subring of the complex numbers. And it turns out that this ring is always either Z, in general, for any tau, this is always either Z, or an order in an imaginary quadratic field. If this tau is the tau that I just picked, the tau which also is in K, then this is always an order in K. Okay? And in fact, this is an order in which all primes dividing the level split or ramify. So notice here that I didn't assume from the beginning that all primes P dividing n split or ramify in K. So it could well be the case that P is inert in K. All what I'm saying here is that these primes P split or ramify in the order. Okay, so if you had chosen from the beginning a K in which some P dividing level is inert, what you get is that this P will be inert in K, of course, but will ramify in O tau, that meaning that it divides the order, the conductor of this order. Okay? And what you more precisely have, so before I said that this is a point which is rational over an abelian extension of K, what you more precisely have is that this point is a point which is rational over what people call the ring class field attached to this order. Okay, so by class field theory, this is the class field whose Galois group is isomorphic via the Artin reciprocity map to the Picard group of this quadratic ring. Okay. So having said this, it's like natural, if you want, to restrict now only to those imaginary quadratic fields K in which all primes P dividing the level are split in K, or if you want, split or ramify in K. I won't consider primes in the level which also ramify in K, just to lighten the notation. So let's assume the following hypothesis that we can call people call it the Heegner hypothesis, which let's assume that all primes dividing the level are split in K. Okay, so one thing that you get is that when you consider this elliptic curve over K, this has an L series, it has an analytic continuation to the complex plane, and it satisfies a functional equation. It makes sense to consider the order of vanishing at s equal to 1, which is the critical point, and the sign of the functional equation, it's easy to compute, and it's -1 in this case, so this order of vanishing is always odd. Okay, so since we believe in the Virchow-Jordan-Dyer conjecture, this means that if it's odd, this means that it's at least 1. So if it is at least 1, this means that there should be at least one non-torsion point on this curve, rational over K. And the big theorem of Gross-Zagier tells you that when you take any of these taus, say that you take tau such that the associated order, or tau, is the ring of integers of K. You get then a point which is rational over the Hilbert class field of K. You can trace it down to K, so you get a point over K. Call it pk. So what the Gross-Zagier formula tells you that the height of this point, the Néronte height of this point, is essentially the first derivative of this function at 1, okay, divided by a period up to some constants, some non-zero constants. So since the height of a point is 0, if and only if the point is torsion, what you get as a corollary is that this point has infinite order if and only if this first derivative is non-zero. Okay. So on the other hand, if we not only know that the rank is odd, but if we assume that the rank is exactly 1, this means that this first derivative is non-zero. So by this corollary, this point has infinite order. So this implies that the group of points of E over K, there is at least one non-torsion point. So the machinery of co-debugging applies to tell you that this is the only non-torsion point. There are no other independent rational points over K on this elliptic curve. So this proves well, the Virchow-Jordan-Dyer conjecture for this elliptic curve over this imaginary quadratic field K. So it's funny that it seems like easier to prove some parts of the Virchow-Jordan-Dyer conjecture when you base change it to K. So then you can ask what happens when you look at BSD over Q itself. So you can manage to use this argument, choosing a suitable auxiliary field K, imaginary quadratic, such that you can apply this formula of Ross and Zagier and the theory of co-debugging to prove, I mean, I'm not going to explain the details now, of course, that if you have any elliptic curve over Q whose analytic rank, that this is the order of vanishing of its L series, is at most 1, that is, it's either 0 or 1, then BSD holds for this elliptic curve. Okay? So this is the role that Heegner points play in BSD, because these p taus and these pk are the crucial tool for constructing these points. So the main point of view that we will have in these lectures is our usual hypothesis will be the L function has sign -1 in its functional equation. Therefore, its order of vanishing is odd. Therefore, it's at least 1. Therefore, there should be a point or a cycle or something. And we would like to construct this point or this cycle or whatever is predicted by BSD or any generalization of the BSD conjecture. So this is mainly the point of view that we'll be having. So in the end, the main goal is, under some hypothesis, we want to be able to construct a point. The several scenarios will be this elliptic curve is defined over Q, but we look at some base change to your favorite number field. You look at an elliptic curve which is not defined over Q, but over some other field, for instance, totally real, over which you know that it is modular, some base extension of this, or higher dimensional generalizations of these conjectures. So this is the main setting of this lecture and the following ones. Okay? Great. So let's try to generalize little by little and see what can we do. So what happens, for instance, if you know that the order of vanishing is odd, but K fails to satisfy the Heegner hypothesis. I said that the Heegner hypothesis implies that the order of vanishing is odd, but the converse is false. No? So there are situations in which the sign is -1. So for instance, this is one situation. Let's assume, just for convenience, that the level of the conductor of your elliptic curve and the discriminant of your imaginary quadratic field K have nothing to do. Okay, so primes in N are either split or inert in K. So factor N in these two set of primes, N plus and N minus. So N plus, you put there the split primes, and in N minus you put the inert primes. So for instance, this is one special situation, quite general. If N minus is square free, okay, so if you want, assume from scratch that your elliptic curve has a square free conductor. So if N minus is square free and there is an even number of primes here, then this order of vanishing is odd, because the sign of the functional equation is always, well, in this square free situations, the number minus the number of primes which are inert in K. So if there is an even number of them, minus this, the sign is -1. So here the Heegner hypothesis is not satisfied as soon as N minus is not 1. There are primes which are inert in K. The Heegner points that I just described, they are not useful, because it is easy to show that they are always torsion. They lead to torsion points on the elliptic curve. Okay, so we have to come up with some other tool in order to construct some Heegner points. And what we do is consider what people call a Shimura curve. Since I'm not going to use Shimura curves very much in these lectures, I'm not going to explain very much the details. The only thing I want you to know is many of you already know what the Shimura curve is, of course. But if this is the first time, let me just say that what you do is, instead of M2 of Q is a quaternion algebra over Q, it's an algebra of rank 4 over Q. Take a quaternion algebra which has some ramification, which is non-split at these primes, at the primes dividing N minus. So since it's non-split at some of the primes, it cannot be split globally, so this is not isomorphic to M2 of Q, this is a different quaternion algebra. But you can play exactly the same game that you play in order to define the classical modular curve. Exactly the same recipes leads you to a different curve, which people call the Shimura curve, attached to this quaternion algebra. This is the role that N minus plays, and N plus plays the classical role of the level. Okay, so if N minus is 1, this is just another name for X naught of N. Okay, this is again a curve defined over Q. And we still, I put it in quotes because it's not exactly true, but since I will go back to this, I will be more precise later, but say that we still have a map, a modular parametrization from this Shimura curve to E. For those who already know the story, the problem is that this Shimura curve has no rational points, and you cannot embed it into its Jacobian over Q. Okay? But since I will explain it with more care in a while, I'll give better details. But for all matters, it's like if we had a modular parametrization. Here on the left, you also have Heegner points, which correspond to. So in the classical case, Heegner points correspond to elliptic curves with complex multiplication. So these curves also parameterize some abelian varieties, some abelian surfaces. So those abelian surfaces which also have CM lead to Heegner points here, and they map to points which behave exactly as the classical ones behave. So we can expect the same kind of formulas, and these were worked out by Zhang. So that's it. We get exactly the same theorems as before in this more general setting. Okay? Okay. So that's what I was saying. So basically what you manage to do is, if you have your imaginary quadratic field K, so you have your curve, elliptic curve over Q, your imaginary field K. Assume that the order of vanishing of the real series of E over K is odd. And now take any subfield of any of these ring class fields, and if the L function of E over this H breaks into a product of L functions, and each of these factors of the L function, the order of vanishing is 0 or 1, then you can apply the same methods and prove the divergence ordinary conjecture for this elliptic curve base change to this h. So I think that what is important to keep in mind is that we know how to prove specific cases of VSD when E is over Q. I take an imaginary quadratic field K, a ring class field over K, and we look at the rational points over this H. Okay, so if the analytic rank is 1, each of the factors is 1, then we know how to. So we are completely at a loss when the rank of vanishing is 2 or more, and we are also quite at a loss if K or H has nothing to do with an imaginary quadratic field. So if I take K to be, for instance, a real quadratic field, none of this works, or any cubic field or whatever. Okay, but there is in one direction that all this generalizes very well. Change now your base field of your elliptic curve. Instead of being Q, take an elliptic curve over a totally real number field. So here the notion of modularity is also well understood. It's not, so if you assume it's modular, so Skinner and Wiles prove that all these elliptic curves over totally real number fields are modular, perhaps under some mild hypothesis, I don't know, but say that your elliptic curve over your totally real field is modular in some suitable sense. You can play the same game. F now is your Q. Take a quadratic extension which is totally imaginary, a CM extension, and you can play exactly the same game to prove very similar things. Okay? The only case in which this doesn't work is when this doesn't work is when the degree of the totally real field F over Q is even, and for instance, the conductor of the elliptic curve is 1. When this happens, then this is the only case in which the same ideas, the same cycle of ideas do not apply, and the only problem is that there is no natural Shimura curve to consider. Okay, I'm not going to go further in this direction, so I'm not giving more details. So just for you to have the idea that everything works quite nicely when the base field is totally real, and the only exception, so this works provided the degree is odd, or there is at least one prime dividing the conductor of the elliptic curve. When this fails, for instance, if you have an elliptic curve over a real quadratic field with good reduction everywhere, meaning that the conductor is 1, this is the typical case in which this strategy doesn't work, and the missing ingredient is that we don't have an analog of the Shimura curve. Okay? Okay, so this is not the main goal of the course, so I leave it here. And well, so the main question remains, so even when E is defined over Q, what happens when we look at the rational points over a real quadratic field or over other fields? This is the main question. What I'm going to do now is to rephrase all this construction of Heegner points in different terms, so that this will allow us to proceed to other constructions. So the Jacobian of X of your modular curve or any curve is the degree 0 divisors up to rational equivalence. And here you have what people call the Abel-Jacobi map, which in this case is an isomorphism, which maps the set of points of your elliptic curve to the lattice. This is what we saw before. And explicitly, this also what I wrote before, it takes any point P to the integral of any differential, the invariant differential on the elliptic curve. It integrates it from 0 to P. And if you have any curve, say your modular curve or your Shimura curve or whatever curve, you can consider its peak knot, its Jacobian. So this is an abelian variety. If X is defined over a field, say Q, this is an abelian variety divided over Q. This guy on the left. And when you look at its complex points, this is this is an abelian variety over the complex numbers. And the way of seeing this as a torus is via the Abel-Jacobi map, which maps any degree 0 divisor on the curve. So the elements on the left are degree 0 divisors on the curve. It maps it to the integration map against D. So explicitly, if you take a basis of differential homomorphic differential forms on your curve, if G is the genus of the curve, so this gives you a set of points, a vector in CG, and this is well defined up to the homology of the curve, because when you integrate and you have to choose a path from one point to another, if you choose one path or another, you may get a different value, and this is accounted for the homology of the curve. And this will be my notation. H10 will mean this. You reverse this, and these are holomorphic forms, holomorphic one forms on the curve. Okay, so you can see Heegner points as divisors on the curve. Let's do again. I will be doing again at least 3 times the example of x naught of n and the classical points, so that we see them in several ways. So let x to be the modular curve. You can embed this curve into its Jacobian by taking any point, and you take as base point the cusp at infinity. So you can embed x into its Jacobian by taking the point p to the degree 0 divisor, p minus infinity, and then you just the fact that E is modular can be rephrased saying that E is an abelian variety which is a quotient of the abelian variety which is the Jacobian of x. So there is a natural projection map from the Jacobian of x to the elliptic curve, and simply maps this divisor D it projects it down to E. And this turns out to be exactly the same formula that I gave you before. Okay? Over the complex numbers, since p naught of x is a torus, and the complex point of E is also a torus, we can regard it like this. X is the modular curve, which is the upper half plane modulo this action. It embeds into the complex analytic version of the Jacobian as before. I take it in tau and I integrate. Exactly the same recipe that I gave before. And if you want to project it down to your elliptic curve, well, if F1, Fg was a basis of modular forms of wave 2, call it F, the first one, the one corresponding to E. So you map down to the first component, and this is your map. So this can be computed in practice. And if now X is not the classical modular curve, but the Shimura curve that you made with your quotidian algebra, the only thing that doesn't work is that since X has no rational points, you cannot embed it in a natural way into its Jacobian, but this is not a problem. You just stay with the second map, which is just as good as before, and the Heegner points that you construct, these are not points on the Shimura curve, but are points on the Jacobian, degree zero divisors on the curve. And that's the way you proceed. Fantastic. So now what we want to do is to, instead of using only a curve, a variety of dimension 1, to consider an algebraic variety of any dimension and see whether we can do anything. So what we need to do first is try to understand what are the analogs of all the ingredients that I was explaining in this more general setting. So this is, of course, a little bit more complicated, so there will be some technical parts that I will try to recall quickly, but you should keep in mind that everything is like the generalization of the one-dimensional setting. Okay, so now I take a variety F, a variety V, which for me will be defined over Q or over the complex numbers, okay, any field of characteristic 0. And, okay, so the one thing that we need, I'm not going to define it now properly, but in the notes that are on the website, there is the definition, and there are many textbooks where this is displayed. You can attach to V what people call the algebraic de Rham cohomology groups. What you need to know here is that these are just F vector spaces. So if V was defined over Q, these are Q vector spaces of finite dimension, and they are equipped with two structures. One is a filtration, which people call the Hodge filtration, which is a decreasing filtration. So it starts with the whole thing, and it goes down to 0. And the pairing, which is alternate between. So if the dimension is D, for any n between 0 and 2D, there is an alternate pairing between these two guys. well, it's a pairing, sorry, so if the dimensions consecutive alternate. Okay, and for curves, which is what we will be using, the field 0 is the whole thing, and the field 1 are only the holomorphic differentials on the curve. So the regular differential forms, regular differential 1 forms on the curve. And here, I put this here because this is one of the interpretations. So since I didn't define for you what the rank cohomology groups are, let me just explain which could be an interpretation of this group for curves. There are many definitions, so the standard one would be in terms of hypercocycles, but for curves there is a very cute definition, which is just consider, if here we consider all regular differential 1 forms on the curve, here take not regular but meromorphic, so you allow poles on the curve, on these meromorphic forms, but the only thing you require is that this differential form is what people call of the second kind, which means that the residues, if it has poles at some finite points, you require that these residues are all 0. At each point, the residue of the pole is 0. Okay, so this stands for the function field of the curve, and if the differential of a function, if you use the Lorentz series are about the uniformizer of any of the points, you really check that the residue at any point is always 0. So this is natural subspace, and you get this. Okay, so this is really computable, and this is what we'll be using in the evenings. Yes.
So in the general setting, are you thinking that he is a smooth?
Yeah. Yeah. Sorry. So here for a variety is smooth. Yeah. So I'm working in the nice setting. Yeah. Okay. So the other. So let me explain you 2 basic comparison theorems, because attached to B there are several cohomology theories. The basic one that we will be using is the round one that I just explained. But you can also attach to it for any prime P what people call the Piadik et al. Cohomology groups. We will denote them this way. And these are also defined for any n between 0 and twice the dimension. And the only thing we need to know here is that these are also finite dimensional spaces. Now, QP vector spaces, it has nothing to do with the base field of the variety. So B can be defined over Q, for instance, and these are QP vector spaces. But the nice thing, the nice structure that they carry on is these are representations. They are equipped with a Galois action of the absolute field, absolute Galois. Okay. In the specific case where the base field is QP, now I define for you 2 cohomology groups, which are both QP vector spaces. Because if the base field is QP, the algebraic de Rham cohomology groups are also QP vector spaces. So you could hope for some relation between them. So again, I'm not going to go into details, but Fontaine has a theory which has a functor which is called decrease, in which case when V has good reduction at P, this decrease of the étale cohomology group is exactly equal to the algebraic de Rham cohomology group. This decrease is what people call the Fontaine's ring of crystal periods over QP. This decrease is equipped with a filtration and with a Frobenius action. So this filtration allows to give filtration on this tensor product, and this is an isomorphism of QP vector spaces together with this filtration. There is also an action of Frobenius on both sides, and this also respects this Frobenius action. But I mean, we won't be using this very much, just for having the idea. And the other comparison theorem that we will be really using in practice in the evenings is that these algebraic de Rham cohomology groups, when the base field is the complex numbers, this is something which is much more basic. This is just the Bethe cohomology, the singular cohomology of the underlying complex variety. Okay. Or you can also regard it as the de Rham cohomology in terms of smooth forms. And this has a Hodge decomposition, where these I and J's are those forms which have I holomorphic disease and J anti-holomorphic disease. And the Poincaré pairing here is completely explicit also. If you have 2 forms, you can pair them by wedging them. This is now 2D differential form. You can integrate it against the whole variety, which has real dimension 2D, so this makes sense. So this is a complex number, and this is the Poincare pairing. Okay, so this was my brief reckoning of cohomology. I mean, that's what we need more or less. Okay, what else do we need to understand in the general dimensional case? We're working with the Jacobian of the curve. So if x was a curve, we were working with a Jacobian. This is also called the Chow group of so Chow 1 of x means cycles of codimension 1. So let me explain it in general. So I take any C, any natural number. C will stand for codimension. And Chow C of our variety will be just the abelian group generated by subvarieties of V which have codimension C. Okay? And the formal sum of those, this is what we call an algebraic cycle of codimension C. So if B is a curve and C is 1, these are just points on the curve, and Chow 1 of x are the divisors on the curve. There is a natural notion of rational equivalence here also as for curves. So this is what we call the Chow group, Chow C of our variety. Okay? Now, the Jacobian of x also has this 0 there. So let's define what is this 0. So we have this map, this CL, which people call the cycle class map, which takes your cycle here. So this is a subvariety of codimension C. So this means, so to say, that it's of dimension D minus C. So therefore, it has real dimension 2D minus 2C. So it gives rise to a natural element in the H sub 2D minus 2C of singular cohomology of your variety as a topological manifold. Okay? So you can look at its class. And since these two guys are isomorphic by this duality that I was mentioning before, you can really look at this cohomology class in this cohomology group. Okay, so it's basically looking at its class in homology. Okay, so you can have that on Chow C this is non-zero. Okay, but on the right this is 0. When this happens, the kernel is what we call the no homologous cycles, and this is the Chow 0. Okay, so this is our definition. So for curves, you get exactly the same as before. And well, we won't be using this again, but just for general culture, one expects that any element on the right which lands in this subspace, so this CC is what in my notation before it was the IJ. So here I and J are all equal to C. So these two spaces have an intersection, and any guy which is on the right should arise from a cycle on the left. So what is this? It is known is that any guy on the left always lands in this subspace of H to C. Okay? What is a conjecture is any guy on the right, it should arise from one on the left, but this is a conjecture, the Hodge conjecture. Okay? Okay. The other ingredient that is missing and we were using before is the Abel-Jacobi map. We use it for curves. So we were relating the Jacobian of a curve, the peak 0 of a curve, to its torus. No? So let's see what happens. So this is what we had before. If x is a curve, Chow 1 x 0 was peak not of x. And on the right, we had this vector space of dimension g, the genus of the curve, modulo this lattice, which is a z modulo of rank 2g. So this is a torus. And the map is the one that I just described. So in general, you construct for any B, any variety of dimension D, and any C, the same C that I was using before, you construct what you call the intermediate Jacobian of this variety. So this is a torus. In general, this is not an abelian variety anymore, but it's a complex torus. Okay. So above we have a vector space, a complex vector space, and below we have a lattice. Okay. So this is a complex vector space modulo lattice. Okay. And this complex vector space is defined this way. So these are, if you remember the Hodge composition, you take the filtration, well, the field C of the cohomology that I introduced before, which explicitly is spanned by those differential forms which have at least in its local expression around any point, it has at least C holomorphic disease. Okay? So this is a complex vector space, and naturally embedded inside this space is this homology group of the variety, which sits inside this space of forms by integrating, as before. So this is a torus. So we have the two ingredients for defining the Abel-Jacobi map. The Abel-Jacobi map in the curve setting had it went from the peak 0 of x to the Jacobian of x. So in general, we have that the chow C 0 of the variety, there is an Abel-Jacobi map, which exactly as before maps any non-homologous cycle on the variety to the integration map. So just take any chain. Since this is not homologous, this means that this is the boundary of something. Take any of these things whose boundary is delta and integrate against any of the forms there in this vector space. So this is well defined. If this is the first time you see this, spend some time at least looking at all the definitions match and they make sense. Okay, and this gives you the Abel-Jacobi map. In general, this is not an isomorphism. Okay, so for curves, this was an isomorphism, but in general, it is not. And I think that if the variety is defined over number field, it is expected to be injective. Okay, so here, yes, so this delta twiddle is any differential chain whose boundary is delta. Okay, so I think this was the recalling of all the ingredients that we are using for curves. I sort of generalized them to any variety. Yes, yes, sure. Yeah, sorry, this is what I said in words. Sorry. Okay, so now the question is, before we had only curves, life was quite easy, and we were able to see a way of producing points on our elliptic curve. How did we do that? We had our modular curve. On each Jacobian, we had some natural points, some degree 0 divisors, which we call these Heegner points or these Heegner divisors, and we were able to map them down to the elliptic curve. These were our points. We would like to be able to do something similar, but when the thing on the left is a variety of any dimension. What is clear is that we don't expect to be able to do so for any variety. I mean, that would be wonderful, but we need some hypotheses, some axioms that should be useful in order to get what we want. So, what we would like to have is, if I have my elliptic curve, say defined over Q, and I want to be able to construct points on E over some number field, the base field is Q, I would like to see the Tate module of the elliptic curve, which is a reincarnation of this étale cohomology group. I would like to see the Tate module of the elliptic curve into some étale cohomology group of our variety. Here, this numerology on the right, I don't think we need to pay too much attention to this. It's what people call a Tate twist of this vector space. It's the same vector space, but with a twisted action of Galois. So we would like to see this Tate model of the elliptic curve sitting within some étale cohomology of the variety. So if you want to pay attention, just look at the numerology, but I don't think you need now to see which are the numbers. These are the correct numbers, but what you want to see is the Tate model of the elliptic curve as a Galois module sitting inside this Galois module afforded by the étale cohomology of your variety. That's what you need. Why do you need this? Because if you believe in Tate's conjecture, which I'm not going to recall its precise formulation, but it's an analog for the étale cohomology of the Hodge conjecture that I recalled before, if you have this, what you get is that there should be a cycle on V cross E of the correct codimension. We don't need to look now at the numerology. I put this question mark on pi because this only if the Tate conjecture holds true, but this guy should exist. And if this pi exists, it could induce the following map. And this is what I really want to pay attention to how this map works. So let's look at the map, the vertical map on the left. it goes from codimension cycles, codimension C cycles on V to points on the elliptic curve. So these are the good news, because this is like a machinery for constructing points on your elliptic curve. If you are able to construct interesting cycles upstairs, you will be able to map them down to your elliptic curve. How does it work? So start with a cycle delta of codimension C, no homologous. Pull it back to the product, to B cross E. Now this is a cycle on B cross E. Okay? Then you can intersect it with pi. See, the only thing I want to make clear is that pi and this pullback, they live on the same variety. These are cycles on V cross E. Okay? When you intersect them, you get a cycle of larger codimension, namely the sum of the two codimensions. And when you project now this cycle down to E, so you do exactly this, what you get is a point. Okay? Great. And the map on the right can be explicitly described via the Abel-Jacobi maps. Okay? Okay. So, since we have this map, this vertical map on the left, we would like to be able to construct interesting cycles on the chow C of V. The nice thing is that this map, although I phrased it in terms of over the complex numbers, because I wanted to compare them to the Abel-Jacobi thing, V is defined over Q, so to say, E is defined over Q, and this map is clearly algebraic, so this is Galois covariant. So if my V is a cycle defined over Q, it gives rise to a point over Q. And if delta is defined over some interesting number field K, so it will go down to a point over K. Okay? And on the right, this is just a complex analytic description which will be useful in the evenings for real computing it. But the important thing to know is that if the conjecture is true, it arises from some arithmetic. Okay, so you want to be able to construct, as we did for Heegner points, cycles on this variety. So you want to choose a nice variety V, over which you know how to construct nice cycles, which you know that are defined over the number field you are interested in. Okay, so since I'm running out of time, so let me just skip a little bit. What I was going to do now is recall once again the construction of Heegner points, the classical point for curves, in this terminology. But since I did already this 2 or 3 times, so let me skip to the second example. So this was my first example, which is the one you already know. And let's go to the second example. Okay? So I want to give you a different example, because if I don't give you an example of a variety of higher dimension, you can then say that this only works in dimension 1. So this example is the one that Massimo Bertolini, Henri Darmon, and Kartik Prasanna work in their recent papers. Okay, so the variety they look at is, for instance, so take x1 of n to be the classical modular curve, parameterizing elliptic curves with a torsion point of order n. And so if n is at least 3, this is a fine moduli scheme, so it has a universal curve. So this is perhaps fancy, but it is in fact basic. This is just a surface, V1, which is an elliptic curve. So this is a surface which is fibered over your modular curve, and the fiber at each point is exactly the elliptic curve which is parameterized by this modular curve. So since a point on the modular curve is an elliptic curve and a torsion point, so the fiber is this elliptic curve with a marked torsion point. Okay, so this is a surface which is called the universal elliptic curve. And over the complex numbers, if we want to be able to compute things, you want to look it over the complex numbers or over the p-adic numbers, but in this course we'll restrict to the complex. And this one, so this is a complex variety, so C is C, and H is the upper half plane with the cusps. So C cross H has dimension 2, and there is this natural action of gamma 1 of n on H and Z2 on C, so this gives you a natural quotient, and this is a complex variety of complex dimension 2. You can, okay. So if you want to see this in terms of moduli, which are the points parameterized by them, so it's as follows. on the right, so this ET corresponds to the elliptic curve parameterized by the points of edge. And for any of these points on the modular curve, for any of these pairs ET, take any point on E. Okay, so this is exactly what you get. And you can do it also for larger R's. So if you take any R, you just take R copies of C. And the fibers, instead of being one elliptic curve, you take the direct product of R copies of your elliptic curves. Okay, so in practice, the base is an elliptic curve, E, with a torsion point, and in the fiber are any choice of R points on your elliptic curve. This gives you a dimension R plus 1. Okay, so this will be my variety. The variety that I was calling D, this will be our V here. Okay, so what did we need it before? So if you remember, we needed this condition that we need in order to be able to apply Tate's conjecture and to be able to produce this diagram which manufactures points from cycles above to points on the elliptic curve below. No? So in order for this to hold, we need to see the elliptic curve, the Tate model of the elliptic curve within the cohomology of this variety. Okay, and this is what you have. Okay, so if you don't mind, let me be a little bit quick here. Just to be concrete, I will take E, for instance, to be an elliptic curve with complex multiplication by a field. Take one of these fields so that E really can be defined over Q. And with these examples, E is the model group of these curves is of rank 1, so it's generated by 1 point. And what it happens is that there is a projector, an element of this Chow group of this product of 2 plus 2 copies of E, such that what you get is that a piece of the cohomology of R plus 1 copies of E sits as a Galois module inside the Etal cohomology of this Kuga-Sata variety. Okay, so this is exactly what we need in order to apply Tate's conjecture. And what Tate's conjecture promises to you, although it is not proof, is that there should be a cycle on the product of the two varieties, E, R plus 1 copies of E, cross our Kuga-Sata variety, which is a cycle of codimension R plus 1. Okay, so with this cycle with us, we can reproduce the diagram that we had in general, and this is what we have. Call XR to be R copies of E cross VR. And remember that our pi was a cycle here. So you can also regard this way. Okay, so R copies of E are in X, and one of the left copies of E is on the other side. So our pi is a cycle here, and now we can apply the thing. My variety that I'm using is this XR, and the diagram that I was explaining before, in this particular case, has exactly this description. Okay? So if we are able to produce cycles on XR, we can map them down to points on the elliptic curve. And if your cycle that you constructed is defined, say, over K, you will get a point on E over K. Okay? So that's the main idea. And just to keep track of the numerology, XR has dimension 2R plus 1. And the important thing is that there is a natural way of generalizing Heegner points to Heegner cycles here. These are Heegner cycles which are of the right codimension, and you can map them down and obtain points on your elliptic curve. And I think I will stop here.